energy can be understood by the curves that we have in figure 3.19. So here it's clearly shown what is the magnetic co-energy and which one is the magnetic energy. So if you have a non-linear BH curve, it is clear from figure 3.19 that the magnetic field energy is not equal to the magnetic co-energy. These two are different quantities. But if we consider a linear BH curve, then magnetic co-energy would be equal to magnetic field energy. And in simple terms, we can write down the magnetic co-energy as I lambda minus the area covered by the field energy, okay, which is given in equation 3.52. So equation 3.52 actually shows the co-energy. So once we know the energy of the system, and if we know the lambda versus I curve of the system, we can actually find out the co-energy of the system. And again, using the co-energy, we can also find out what is the force acting on the system. So using some mathematical manipulation, we can deduce that the force acting on the plunger is rate of change of co-energy with displacement at constant current. Okay, and if we see the previous analysis and this analysis, we can say that the force or the torque acting on the system is minus rate of change of field energy with respect to angular displacement for constant flux linkage, or rate of change of co-energy with respect to angular displacement at constant current. So equation 3.56 gives the equation of torque. So the force and torque are very related quantities. So if you consider rate of change of co-energy with respect to linear displacement, we have force. If you consider rate of change of co-energy with respect to angular displacement, we have torque. Okay, so if we want to use co-energy, we should ensure that the motion of the plunger has taken in such a way that the current is held constant. If we want to use field energy, then we have to assume that the motion of the plunger has taken in such a way that the flux linkage lambda remains constant. And this is what we can also see in some of the previous figure 3.18. So if we want to use co-energy, we have to go from point A to point C. If we want to assume field energy, if we want to use field energy for force calculation, we have to go from A to D. In going from A to C, my current remains constant. If I go from A to D, my flux linkage remains constant. Okay, so this is in short the principle. And similarly, we can do the analysis of a doubly excited system which has a rotational motion, and this is actually shown over here. So this was discussed in our previous webinar, so I will not go into details of it, but yes, instead of a linear motion, if we have a rotational motion, then we have a simple reluctance machine shown here, and these are the two extreme positions of the rotor for which we will have different values of the reluctance. And then if we see here, this is the in figure 3.23, we see the variation of the reluctance with the rotor angle, and this is the animation which shows that how the reluctance varies as the rotor keeps on moving. Okay, so this was covered in detail in the previous webinar, so if somebody has missed that, then they can please visit the webinar and have a look at it. What we do now is actually we will be working with something which is known as the basic virtual lab. Okay, so these are some of the exercises that we have created, and here we have the first problem which explains the principles of flux linkage and so on. So if you see here, we can change the relative permeability of the system, we can change the input voltage, we can change the number of turns, we can change the mean flux path length, then we have the area of the cross section, and then we change the air gap. So we have set all the values, and once all the values are set, you can see on top that three different curves are shown on the left hand side and three different curve possibilities are there on the right hand side. So let's look at the input electrical power. So this shows the curve of the input electrical power. So here you see there are three variations of the current that took place. So initially the current rose, went to a steady state value, then we increased the resistance, the current dropped, then we decreased the resistance, the current rose, and then we again increased the resistance, I'm sorry, and the current reduced. So details of this are there inside the book, but here what I want to demonstrate is that as soon as I change my voltage, for example, my input electrical power changed. So if you observe the y-axis carefully, the y-axis has changed. If I change my relative permeability, okay, by certain factor, so you will see that my x-axis changes, because by changing the relative permeability I am changing the inductance, and with change in the inductance the rise time and the fall time of the current would actually change. Okay, and similarly I can also plot here on this curve power dissipated across the resistor, and then we can have the curve for the power absorbed by the inductor, and same way we can see all the differential input energy, differential energy dissipated across the resistor, and the differential energy stored in the inductor. So whatever I vary, if I vary my air gap length, you would see that there would be variation in the parameters. So if you have seen the y-axis carefully, the magnitudes changed because change in the air gap resulted in change in the inductance, and once the inductance changes, then my current's rise and fall time would change. Okay, the amount of magnetic energy that can be stored would also change. So you see all those kinds of changes. So it's kind of a demonstration. It goes hand in hand with the book. So we have seen the previous in the book, the section where we were explaining all these concepts, and then the student and even the faculty colleagues can use this kind of an exercise to see how the entire dependency of the results is on the input parameters. And now what I would do is actually I would like to show you some exercises. So we have multiple exercises based on the principles that we have discussed so far. So here we have the same plunger problem, force acting on a moving plunger, and here we give some parameters. Okay, so I define number of turns to be 1000, for example, the current through the coil to be 10 amperes. Then I have the air gaps. Details of this are given in the instructor manual of our entire course package. So I have 2 air gaps and I feed their values. All the values are in millimeter. Then the width of the plunger 150, and then the length of the plunger, let's say 100, and then the permeability of the free space, so I'll just approximate it. I'll just make an approximate value, and then the height of the plunger, it's again 10 millimeter, and then we press on calculate. Okay, so here we on in the first row we have the position of the plunger. What one has to do is actually one has to calculate the inductance, and for inductance the calculation, the formula is given here on top of the screen, okay, in step 1. So one has to actually calculate that and put the values here in these columns, and then the program will automatically check whether the calculated values are correct or not. But what I do is, just to save time, I will fill the row, and if you see here, this is how you get the variation of the inductance with the movement of the plunger. In open position, that is x is equal to 0, the inductance was very high. Okay, oh sorry, x is equal to 0 means the plunger is completely closed, and at certain other value of x, 150 millimeter, the plunger is far away from the remaining magnetic circuit, so the inductance is low because our air gap has increased. So then after that we go to the next part. We are supposed to calculate the energy. So energy is half Li square, and here we have assumed the motion to be at constant current because I have given a fixed value of current. Okay, so I know the inductance value at each point of the plunger, I know my current value, so I can calculate half Li square. So let's just fill up the value, and here I get my curve for the energy. Then we go to the next part. We have to find out the co-energy. So co-energy is lambda I minus the field energy. So one has to do the calculation. In the real problem, whenever the student is working with that problem, he or she has to fill in the values and the program automatically checks. But here what we do is we will just enter the values to save time, and here we see we have the co-energy. Now if you see here, we have the co-energy exactly equal to the field energy because we have assumed linear motion of the plunger. Okay, and sorry, not the linear motion of the plunger, I'm sorry, it's the linear BH curve of the plunger. Okay, or the linear lambda versus I curve. We have not considered any kind of a magnetic saturation. So if magnetic saturation is avoided, then field energy is always equal to the co-energy. So then now let's go to the next part. We have to find out the differential inductance, okay, or derivative of the inductance with respect to position. So we have X on top, and then we have the second row, which is the inductance. So we can easily find out the derivative, a numerical derivative, okay. So y2 minus y1 divided by x2 minus x1, that gives us the numerical derivative. So one has to fill those values over here. I'll just automatically fill it, and then we get the numerical derivative, which is all the negative quantities that we are going to get. Okay, and then we go to the next step, and here we have to calculate the force. So in the text we have seen the force actually was given by, let's go to the part of the description that we had. Okay, so the force was given by half I square rate of change of inductance with the position. So all those things we have calculated, and eventually one can calculate the force. The current is constant, and then the rate of change of inductance was calculated in the previous step. So I just fill in, and then I get the value of the force acting on the plunger. Okay, and this is the final step of the calculation. Similarly, there is some other interesting examples that we have. So if we go here and we see problem number 2, so here is a specific case for a constant current. So I'll just go through this very fast just to demonstrate the difference between a constant current motion and a constant flux linkage motion. So this is a constant current motion. I gave a fixed value of current 10 ampere. So I find out the inductance. So the inductance variation is given here. It's 1.2 plus some exponential of position. Okay. Then I go, this is the inductance variation for the closed position and the open position. And then finally I find out the flux linkage. Okay. And then I go to the next part, energy. Then we calculate the co-energy, and then we calculate the force. Unfortunately, due to scaling, I can't have the exact figure of the force here on my screen. Okay, but one can check here. So it is minus 47.58, the first value, and minus 43.05, which is the second value. Now what I do is I take an example, which is force with constant flux linkage. Okay, so if I take the constant flux linkage part, then I can see the difference 0. So I do that and press calculate. So let's fill some values, then we go to next step. I calculate the current, okay, because here now my current is not going to remain same. As my plunger changes the position, my flux linkage remains constant, so I have to calculate the current for each plunger position. Okay, so if you see here, my current does not remain constant as the plunger moves. And then I go to the next step and I calculate the energy. Okay, and then I go to the next step and I calculate the co-energy, and then I go to the next step and I calculate the force. So unfortunately I don't have the graph, but I wanted to show you the nature of the graph. If we have a constant current motion, then the graph of the plot of the force would be some kind of an exponential function. Whereas if we have a constant flux linkage motion, then the force would exhibit some kind of an S-shaped function. Okay, so force as a function of position of the plunger would be S shaped English alphabet S in case of constant flux linkage motion, and in case of a constant current constant current motion, it would be kind of an exponential curve. So the nature of the curve itself changes if you assume a constant flux linkage motion or a constant current linkage motion. So these are some of the exercises which are also available with the entire material, and here I would like to take a small break to discuss questions with you. If you have any points or anything that you want to discuss with me, then please do let me know before I would finish this webinar with my last presentation, which is a quiz on the topics that we have discussed. So if you have any questions, then please do ask me. Anything that you would like to know or you would like to ask? I'm pretty sure this was a very short time to cover so much of ground, but yes, if you would like to have more discussions, we can organize the different webinar, and moreover the details are there inside our complete e-learning package, so which is available. So please do ask any queries or questions that you have before I show you the quiz, which is the final part of this package.